Okay, this is lecture 13, part B, and this is going to be the big trig review, and it's motivated by trying to calculate this limit, which is a very important limit, and we're going to be doing some things with it in the future. It's the limit as h goes to 0. Well, actually, let's change variables. Let's call it x. Limit as x goes to 0 of the sine of x over x. You remember in the last video we looked at sine h over h as h goes to 0, but x is a little easier to write and it's more comfortable for everybody anyway. And the point of this is that the limit of this expression is going to turn out to be 1. But it turns out that that's not correct unless the angle that you're measuring with is done in radians. And why that should be is kind of interesting and leads to the review of trig that we need to talk about. So let's look at some things in trig that everybody's supposed to know. And actually it all starts on the unit circle. Let's go there. So on the unit circle, everything really takes place right here on the unit circle. Doesn't look like a circle yet, but I want the x and the y axes, more or less. Sorry about the waviness of the lines. I'm not real good at drawing. Okay, so this is a circle, something called mathematical license. If I say it's a circle, it's a circle. All right, but it's the unit circle, and what that means is that the radius of this circle is 1. So that's why it's called the unit circle. But everything in trig happens on the unit circle. And the reason is because if you take an angle, start at the origin and just go up somewhere at any angle, like there, let's say, and look at what happens when you drop a perpendicular from this point. Okay, what you get is a little triangle in here. And it's a right triangle because I dropped a perpendicular. Now you remember from trig, most of you learned things like SOHCAHTOA. So what does that mean? It's the sine is the opposite over the hypotenuse, etc. So I want to look at the sine on this triangle. So if you think of the sine of the angle, and I'm going to call the angle x, the sine is, well, the sine is the opposite over the hypotenuse, always, a definition in terms of right triangle trigonometry. But if you look at this triangle and make this your angle, then the sine would be the opposite, that's this, over the hypotenuse, which would be that. And notice that the hypotenuse is the radius of the circle, so that's really 1. So from here to here is 1. It's also 1 from here to here, and as I drew a minute ago, it's 1 all the way over there. It's not 1, however, from here to here, and it's not 1 from here to here. Okay? So it's 1 when you measure the radius of the circle. So this hypotenuse of this right triangle is 1. And so if you look at the sine of this angle, opposite over hypotenuse would be this side, being the opposite, divided by 1. And so in fact, you could label this side right here as the sine of the angle. So this is extremely useful because it gives you a geometric interpretation of what the sine is. You can imagine this vertical segment right here changing as you scrunch the angle. So imagine pushing this ray down so that the angle gets smaller and smaller. You can see this vertical segment getting crushed down and getting down to 0, which tells you also that the sine of 0 is 0. And as you push up on the angle, you can see this segment getting bigger and bigger, and it's never going to get bigger than the radius of the circle, obviously. So the sine just builds its way all the way up to 1. And this is very nice. It gives you a nice geometry picture, a geometric picture to keep in mind. While we're at it, you might remember that the cosine is the adjacent over the hypotenuse. So if I write adjacent over hypotenuse and look at the triangle that I was just looking at, the adjacent is this side, the horizontal, and the hypotenuse is that one, which is 1. So the adjacent is actually the cosine. This segment is the cosine of the angle. And so you can visualize the cosine. So when you push down on this angle, you can see the cosine getting bigger. And so when the angle gets all the way down to here, you can see that the cosine is almost the radius of the circle, which would be 1. So in fact, when the angle is 0, the cosine of 0 is 1, which is why you should not forget that, because you can picture the cosine on the unit circle as this horizontal segment. So when somebody asks me a question about what's the cosine of 0, what's the cosine of pi over 4, I think of the unit circle, and I think of this picture, and I imagine what the cosine is doing, and the cosine stretches all the way to 1 when the angle is down here like this. So cosine of 0 will be 1, and the cosine of 90 degrees will scrunch down to 0. As the angle gets bigger and bigger, as you push this ray this way, you're forcing this horizontal segment to get smaller and smaller. So that's the cosine. Now there's another triangle. There are many other triangles in this picture, but I want to look at one that starts here at the point 1, 0 and goes straight up and goes to this point and then goes back down to the origin and back across along the x-axis. Right? This big triangle right here, now the hypotenuse of course is not 1, it's much bigger than 1, but notice that the base of this triangle is 1, it's the radius of the circle. And think about what the tangent is. The tangent is the opposite over the adjacent. So opposite would be, this would be the opposite. The adjacent this time is 1, so the tangent is located right out here. It's the length of that segment right there. And that is very cool because again you can visualize the tangent segment geometrically. So if you push down on this angle, you see that the angle becomes almost 0 and the tangent becomes almost 0. This vertical segment becomes almost 0. Incidentally, so does the sine, which we talked about a minute ago. If you push up on this angle, the tangent gets bigger and bigger. In fact, it's already, in this particular picture, it's already bigger than the radius of the circle. So the tangent is bigger than 1 here. And as you make your angle even steeper, close to 90 degrees, this tangent is going to get huge. In fact, as the angle approaches 90 degrees, the tangent will blow up. The tangent will be infinite in its value. Now, I'm not going to do the other 3 trig functions, but believe me, they are on the unit circle also. They will just muck up the picture, and I don't really need to look at them in terms of what I'm doing. Remember, I was doing this problem. I haven't even started it yet, but this is the part of trig that you need to remember. The sine and the cosine and the tangent are all there on the unit circle for you to notice and to see what they do. Speaking of the unit circle again, I neglected to mention radians as being so important because with radians you actually know what you're talking about. With degrees it actually takes very advanced math, like graduate level math, before one can define what you mean by a degree. In radians it's very easy to define what radians are. Radians are just distances. Radian measures distance along the unit circle. So if you're talking about a 1 radian, that would be 1 unit around this circle. So how far is this circle all the way around? Well, we know the circumference of any circle is 2 pi times the radius, or pi times the diameter, right? So the circumference of this circle would be 2 pi times 1, or 2 pi. So the distance all the way around is 2 pi. So the distance halfway around the unit circle would just be 1 pi. Very, very important. Going from here, halfway around the circle gets you a distance of pi. Pi is about 3, a little over 3. So if you're going only this far, you'd be going a distance of pi over 2, which would be about 3 divided by 2, or about 1.5. So 1 radian would actually be somewhere in here. So the angle that I drew here is probably a little short of 1 radian, but if you want to know a ballpark figure for 1 radian, that's somewhere in this neighborhood, right? It's a distance. It's how far you'd have to walk on the unit circle. The unit circle being the circle of radius 1. And the distance halfway around the unit circle would be pi. So that's what radian measure is all about. Now notice that there are some interesting things that happen here, especially for you engineers, when the angle is very, very small. Okay, for very small angles, let me just draw the picture down here. If the angle is very small, okay, when you drop these perpendiculars along the circle, you drop one perpendicular here, and then here's that tangent segment that's on the, oh, incidentally, that's why they call this the tangent. This function is called the tangent because of this geometric interpretation that it's the length of the tangent segment to the circle. This segment is actually tangent to the circle at the point 1, 0. That's how it got its name. Anyway, this vertical segment is the sine of the angle. This vertical segment where you hit in here would be the tangent of the angle, and the length of the curve is the radian measure of the angle. Now, you can't see it real well because of the way I've drawn it, but on this triangle here that we've been playing with, oops, this big one, this is the tangent, this is the sine, and the angle would be the distance along here. So that is the radian measure of the angle. It's the distance on the unit circle. So that's kind of an important thing to know, all right? It's useful for you engineers because if you look at this particular picture where the angle x, let's say, is very, very close to 0, if you're talking about small angles, then look at the difference between the sine of x and the tangent of x. If you actually go to a calculator and punch these numbers in, you will find that the sine of x is very, very, very close to the tangent of x for very small angles. In fact, the distance around the circle is also about the same. So in fact, x is approximately, the sine of x is approximately the tangent of x. So if you want to test this out, make sure your calculator is in radians, set in radians, and pick a small number for x, like 0.001 or 0001. That will be really good. If you punch this in, I will bet you large amounts of money that, and I haven't tried this, but that the sine of this number is about 0.0001, and the tangent of this number is approximately 0.0001. And what this tells you is that if you've got these expressions as part of very complicated expressions, and they're hard to deal with, but you happen to know that at this part of your calculation, x is a small number, you can replace x, you can replace these complicated things by x, which would be much simpler than having to deal with trig functions. So this is an approximation that engineers and other people in practical areas find very, very useful. It's something to just file away. No extra charge for that. All right, so we're ready to begin the argument about why the limit of the sine of x over x is equal to 1. So here is what we're going to do. We're going to look at this picture again, only on a clean screen. So here's this triangle again. Well, first of all, here's the unit circle. And on the unit circle, of course, the radius is 1. And I'm going to draw an angle. And I'm going to draw this tangent segment just like I had before. Okay, but I'm also going to draw a triangle that I did not have before. I'm going to draw a segment that goes here like that. And to make sure that we know what we're talking about, I'm going to label all of these points that I've drawn on the unit circle. So this one is O, which stands for origin. This is A, this will be B, and this will be C. I'm going to be talking about different parts of this picture. And what I want to look at are, well, remember that this is the unit circle, so the radius of the circle is 1. So I want to look at triangle OAB. And on the outside, I want to look at triangle OAC. That's the big triangle. And in between those two triangles, there is another geometric figure. It's a geometric figure that starts here at the origin, goes out to B, and follows the curve of the circle down to A, and then cuts across to O. And that's something that we call a sector. A sector of a circle is something that looks like that. So the sector that I'm talking about is sector OAB. All right? And what I want to say is that the triangle that I first talked about, OAB, is contained in. Now, mathematically, we have this symbol for contained in, is a subset of. If you haven't seen it before, don't worry about it. Just replace it in your head with is a subset of, or is contained in. So the triangle is contained in the sector, and the sector, in turn, is contained in the big triangle. I don't think that's any surprise to anybody else. Now, these are geometric figures, each of which has an area. Therefore, the area of this triangle has to be less than or equal to the area of this sector, which has to be less than or equal to the area of this big triangle. Okay? So the area of this guy as a triangle has to be less than, because it's contained in the sector, and the sector in turn is contained in the big triangle, so its area is less than or equal to. Okay, so what I need to do is calculate those areas. And the two triangles are pretty easy. The area of a triangle is 1/2 base times height. I hope you all remember that, because we're going to use that a million times. So the area of this triangle is 1/2 the base. Well, I know what the base is from O to A. That's the radius of the circle. So 1/2 times 1. And the height, well, I haven't drawn the height yet, have I? How long is that? Well, you've seen that before. That happens to be the sine of the angle. The angle which I've not labeled, but we're going to call the angle will be x radians. So in other words, the distance from here, that is A, along the circle to B, so that distance, the arc length from A to B, is x. That distance is x. So 1/2 base times height, the height is the sine of x, that segment from what we just looked at a few minutes ago. All right, that's going to be less than or equal to the area of the sector. Let me come back to that and do the area of the outer triangle, which again is 1/2 base times height, but this time we have 1/2. The base is still 1. It's the same base as the smaller triangle, but the height now is from A to C, and you all know what that is because we just looked at that a couple of minutes ago. That is the tangent of x, the tangent of the angle, the length of the tangent segment. Now, how about this sector? I don't know that anybody, well, I don't remember a formula. I still don't remember it. Even now, I do not remember the formula for the area of a sector. But that's something that's easy enough that I can do it pretty quickly, because the area of this is like the area of a slice of pie. My wife just cut a piece of pie, so it's on my mind. So here's the area that we're talking about. How much area is in that sector? Well, I can figure out how much area is in the whole pie, the whole circle. The area of a circle is pi r squared. And the unit circle has radius 1, so the area of the whole circle for the unit circle is just pi. Isn't that nice? Pi times 1, in other words. So the whole pie has area pi. There's something fitting in that. All right, so the whole area is pi, but I don't have the whole area. I just have this much of it, because that's how much she cut. How much did she cut? Well, we called it x a minute ago. It's the distance from here to here, the distance from here to here. So how much of the pie did I get? Well, I formed the ratio of x to the whole distance around. What's the whole distance around? We calculated that a minute ago too. That was the circumference. Remember, circumference is 2 pi times the radius, which is 2 pi for the whole circle, for the unit circle. So it's 2 pi all the way around, and so the part that I was given was x. So x over 2 pi is the percentage of the whole pie that I got. Right? This is x. This is how much I got. The whole pi is this much, and it has circumference 2 pi. So the percentage, the portion of the pie that I got, was x over 2 pi. So the area would be this percentage of the whole area, which is pi. So I just take this percentage and multiply it by pi, and that reduces to a nice easy number, x over 2. So if you measure your angle in radians, the area of a sector is really simple. It's just x over 2. Okay, now we can do some algebra and some trig. Put in the tangent is equal to sine over cosine right here. So this is sine x over cosine of x. And then multiply everything in sight by 2 to get rid of all those nasty 2's, 1/2, and you end up with sine x less than or equal to x less than or equal to sine x over cosine of x. Now, let's suppose that we stay in the first quadrant for simplicity. What that means is that all of our sines and cosines and tangents and so on will be positive numbers. That's going to be nice for me. And then it turns out it's not going to matter even when we went into the negative areas because of the way the calculations work out. But for now, let's just assume that we're in the first quadrant, and we'll prove it for the first quadrant, and then it's still going to be true in other areas. But what if I do something a little bit weird? I'm going to multiply everything in sight by 1 over sine x. So if I multiply everything by 1 over sine of x, I get 1 here, and I get x over sine x here, and I get 1 over cosine x here. Okay? That just cancels off those signs and sticks a sign in here, which makes things a little bit simpler. Now, one last trick that I need is an algebra trick, which you may never have seen before. But here's the thing. If all of these numbers are positive, and you've got a over b less than or equal to c over d less than or equal to e over f. Oops, e over f. What happens if you flip everything upside down? If you go b over a, d over c, f over e. Well, by simple algebra, I mean, it takes about a few lines to do it, and I'm not going to, but you can do it if you need to, if you don't believe me. Flip over the fractions, the relationships reverse. So if you had two fractions related as less than the first time, flip them over. It's now the first one flipped over will be bigger. I don't think anybody was surprised by this kind of result. The interesting thing is it holds even if you've got 3 of them in a row, like I've got right here. So if a over b is less than c over d is less than e over f, flip everything, the inequalities reverse to maintain the truth of the sentence. Well, I've got an inequality here, and I'm going to flip everything upside down, and everything's positive, so I'm going to get this inequality, which is a little bit difficult because I've got bigger than or equal to, and I don't like that too much, but we'll deal with it. Sine x over x, bigger than or equal to cosine of x over 1, which of course is just cosine of x. And now, ladies and gentlemen, we are ready to do the following. What's going to happen if I look at this inequality and ask what's going on here as x gets closer and closer to 0? Well, here's this function. Recognize this guy? That was the original question. That was the limit that we were supposed to figure out at the beginning of the lecture. What is the limit of sine of x over x? And I'm claiming that it's 1, but we don't know that for sure yet. And here we are now seeing the function sine x over x trapped between two things, one of which is 1 and the other is cosine of x. So as x goes to 0, what happens to the left side? Well, 1 is a constant, so the answer to that is nothing. What happens to cosine of x, however? As x gets closer and closer to 0, we saw this on the unit circle, cosine of x is getting closer and closer to 1. And now we whip out what we saw in the second chapter, as the squeeze theorem. And I mentioned back then that there was a time when we would use it. And it says if you have a function that is squeezed between two other functions, both of which have the same limit, then the one that's in between is going to have that same limit too. It's crushed between a rock and a hard place. So this cosine curve is scrunching into 1. It's like the walls closing in on this sine of x over x, and the closer x gets to 0, the closer this wall, slides in towards 1. 1 isn't moving at all, but this is the moving wall that makes its way in towards 1 and crushes sine of x over x into 1. And that does it. Now, it does it only for positive values of x. But you know what? If you look at this inequality right here and ask yourself, what would happen if you made x negative? Think about it. If you just replaced x by its negative here and here and here, the cosine is what we call an even function. Remember, the graph of the cosine looks like this. It's symmetric with respect to the y-axis, which means that if you plug in a positive x and a negative x, you're going to get exactly the same answer. It's symmetric with respect to the y-axis. So it doesn't matter, you're going to get the same answer if you plug in minus x. And sine x over x has the same property, because if you plug in the negative of a number here, that negative would work its way out of the sign. That's one of the properties of the sign, one of the trig identities. I'll write it down. Sine of minus x is the negative of sine of x. Sine is known as an odd function because it does exactly this. So that minus would come out and cancel with the minus that you put down here. And all that said means that this inequality that we have right here is true whether x is a positive or a negative number. And so that tells us that even when x is approaching 0 from the negative side, this sine x over x is still getting crushed between cosine of x and 1. And so, in fact, the limit of sine of x over x is 1 no matter what. Okay, a couple of other things that are, well, let me first talk about what other types of problems you can do now with this sine of x over x business. You can also calculate the sine of other things, like pick a number, let's say 7. What would the sine of 7x over x have as its limit as x approaches 0? Well, here you've got to do this, you've got to learn this trick. How can you make this look like sine x over x? Just keep sine x over x in your head. What is the limit of sine x over x as x gets small? What if you just stuck in a 7x down here in the denominator? Well, you can't do that, can you? Well, you could if you stuck it up here also, so that nothing would happen. In other words, you're not changing the problem. That's the trick. Put in the 7x that you need, and then cancel it back out before anybody notices. Actually, you can even do it without the x, because all you need is the 7 down in the denominator. All right, that tells us the following. In fact, let's do it that way. This is too complicated. Just stick in a 7. Multiply top and bottom by 7. And here's what you'll get. The 7x on the bottom is what you want, and the sine of 7x on top is what you want, and the extra 7 that you needed to make it all work, just pull it out of the limit, because the limit of a constant is the constant times the limit of the function. So we have the limit as x goes to 0. And now you ask yourself, what happens as x goes to 0? 7x is also going to 0. 7x is going to 0. So the sine of 7x over 7x is behaving just exactly like sine x over x, because the argument in each case is going to 0. So sine of 7x and 7x are going to 0 in exactly the same way as sine x over x are. Now they're going a little faster, but they're in sync with each other. So this limit turns out to be 1. And so the answer is 7. So our original question, what is the limit of sine of 7x over x? Well, the answer turns out to be 7. And you can use this trick so many different ways. What if the question is, find the limit as x goes to 0 of sine 2x over sine 3x? How are we going to do that? Both are going to 0, so this is bad news. Well, you stick in the x's that you need. So what do I need? I need a 2x down in the denominator, and I need a 3x up in the numerator. The 3x to go with the sine of 3x, the 2x to go with the sine of 2x. Now I can't just stick those in there. So quick, cancel them out. All right? So we will multiply by 2x over 2x and multiply by 3x over 3x. And now regroup, and here's what we're dealing with. We've got the limit still as x goes to 0 of sine 2x over 2x times 3x over sine 3x. And then I've got this other stuff left over. Let's see, the 2x was here that went to that, so that's taken care of. And this 3x got taken care of, but I still got this 2x and the 3x left, but that just reduces to 2/3, and so 2/3 just comes out. And now I can say, what's the limit of this thing? And it turns out the limit of this thing is exactly 1, because it's just the same as sine x over x. What's the limit of this thing? Well, it's 1 also, because it's just the reciprocal of something that goes to 1, so it has to go to 1. So the limit of that is 1 as well, and so the limit in the end is just 2/3. Now I know what 99% of you are thinking. Oh look, it's just the coefficient of sine divided by the coefficient of sine. Yeah, it worked out that way, but don't trust that. There are going to be problems that don't do that exactly, especially when cosines are involved. So just remember the trick of putting in what you need. Like you needed that 2x down here in the denominator because it had to pair with the sine of 2x. So you put it in, but you can't just do that. That would change the problem. So you put it in and you quick take it back out again. And the same thing for the sine of 3x. You regroup and then see if something good happens. And sometimes, like in this problem, very, very good things will happen. Okay, one last thing about trig, and then we call it quits. I promised that I was going to show some of you how you do these standard angles. Standard angles being 30 degrees, 60 degrees, 45 degrees, and they rely on knowing things about 30-60 triangles. So let's draw what is approximately a 30-60 triangle. And remember a basic fact that on a 30-60-90 triangle, the short side happens to be half the hypotenuse. So if this is the hypotenuse, this will be a 30-degree angle. This is the 60. The short side is the side opposite the 30. That will be half the hypotenuse. And the long side is the square root of 3 over 2 times the hypotenuse. Well, I don't really care about the hypotenuse because I'm doing everything on the unit circle. So the hypotenuse is 1. So the important numbers to remember are 1/2 and square root of 3 over 2. That's the short side of a 30-60 triangle and the long side of a 30-60 triangle. For a 45-degree right triangle, the angles are both 45 degrees. And the thing to remember there is that each of the sides is the same, and it'll be the square root of 2 over 2 times the hypotenuse. Each side is square root of 2 over 2 times the hypotenuse. So if the hypotenuse is 1, then these two numbers are square root of 2 over 2 and square root of 2 over 2. So those are the magic numbers to remember for 45-degree angles. So taking it back to unit circle, if you think of an angle like pi over 3, where is pi over 3? Well, pi over 3 is 1/3 of the way to pi. Pi is halfway around. So 1/3 of the way to pi would be somewhere around there. a third of the way to 180 degrees would be 60. So yeah, pi over 3 is 60 degrees. So what is the cosine of pi over 3? It's something you should just know almost instantly, because you picture this pi over 3 angle, which is pretty steep, 60 degrees, and you picture this triangle on the unit circle, and the cosine is the horizontal segment, which would be the one that's opposite the 30, because this guy is 60. So this would be the short side of a 30-60 triangle, so the answer is 1/2. That makes the sine of pi over 3, pi over 3, the long side of a 30-60 triangle, and so that would be square root of 3 over 2. How about if we go this far around the unit circle? That would be 3/4 of the way to pi, 3 pi over 4. All right, that's obviously going to give us a 45-degree angle somewhere. But if you draw your triangle here this way, drop your perpendicular, now you've got a triangle that looks like this. The picture is still the same. The vertical segment is still going to be the sine of the angle. And it's measured in the up direction, so it's positive. But the horizontal segment is now measured in the negative direction. So this is a negative value. So the cosine is negative in the second quadrant. So if you want to know what is the sine of 3 pi over 4, you just have to think 3 pi over 4, 3/4 of the way to pi, which is equally dividing into 4 pieces, this half of a circle. So dividing into 4 pieces, each of which is 45 degrees wide. So this has to be a 45-degree angle. So this triangle has to be the 45 degrees isosceles right triangle. So the sine would have to be this vertical segment, which, you remember the magic number, square root of 2 over 2. And the cosine is about the same thing. Cosine of 3 pi over 4 would be also the square root of 2 over 2, except it's measured in the negative direction. So it's minus square root of 2 over 2. And you can play this game with any angle that's a multiple of pi over 6. Let's do 7 pi over 6. 7 pi over 6. What are we talking about? We just go 7/6 of the way to pi. This is 6/6 the way to pi, and one more takes us to 7/6 of the way to pi. So we have a relatively short angle here, which will be 30 degrees. 1/6 of the way to 180 is 30. So this is 30 degrees beyond 180. The vertical segment will be the sine, and you notice that's now measured down, so it's going to be negative, and the horizontal segment is going to be negative as well. It's measured to the left. So if you ask what is the sine of 7 pi over 6, the answer is the vertical segment here, which is the short side, a half, except that it's negative because it's measured in the negative direction. Similarly, what's the cosine of 7 pi over 6? Well, that's the horizontal segment, and it's measured in the negative direction, but it's the long side of a 30-60 triangle, so it's going to be square root of 3 over 2, and of course negative because it's to the left. Okay, that should be enough review for trig for us for now, and we'll see you later.